In this video, we will see two types of flip-flop. The first one is SR flip-flop and the second one is JK flip-flop. SR flip-flop is also called set-reset flip-flop. In this flip-flop, we have two inputs, set and reset. For these two inputs, we get two outputs, Q and Q prime. These two outputs are the complement of one another. When we give set equal to 1, then the output Q becomes 1. This output gets stored inside the flip-flop. Again, when we give reset equal to 1, the output Q becomes 0. Then this 0 is stored inside the flip-flop. So set basically stores 1 inside the flip-flop and reset stores 0 inside the flip-flop. Here we can see the circuit diagram for set-reset flip-flop. Firstly, we perform AND operation of the set and reset input along with the clock pulse. Here, when the clock pulse is high or 1, the flip-flop works according to the input. But when the clock pulse is 0, the flip-flop stops working. So the clock pulse basically controls when the flip-flop will be turned on or off. So when set and reset are given as input to the AND gates along with the clock pulse, then if the clock is 0, the result of both the AND gates are also 0. But when the clock is 1, we get the set reset value. Then these two results of the AND gates are passed into two separate NOR gates. We can see that Q prime and reset are the inputs of one NOR gate and Q and set are the inputs of another NOR gate. These Q and Q primes, which are working as the input of the NOR gates, are the previously stored value inside the flip-flop. So suppose if we saved 1 inside the flip-flop previously, then the value of Q in the NOR gate will be 1 and Q prime will be 0. Again, if 0 is previously saved in the flip-flop, then Q will be 0 and Q prime will be 1. We know that if one of the inputs of the NOR gate is 1, then the result is automatically 0. So let's assume that we have set equal to 1 and reset equal to 0. When the clock pulse is 1, we get 1 and 0 from the AND gates. Since one of the input of the first NOR gate becomes 1, so the result will automatically be 0. Therefore, we get Q prime equal to 0. This 0 will be passed as the input of the second NOR gate. So in the second NOR gate, the two inputs are 0 and 0. So the result is 1. So we can see here that when set equals to 1 and reset equals to 0, we get Q equals to 1 and Q prime equals to 0. This 1 will be stored inside the flip-flop. Now if both set and reset becomes 0, it will work as a no change operation. This means that the previous value that is stored inside the flip-flop will not change. So Q will remain as 1 and Q prime will remain as 0. Now let's make reset equal to 1 and set equal to 0. Then firstly, from the NAND gates, we will have 1 and 0. After that, since one of the input of the first NOR gate is 1, the result will automatically be 0. So we get Q equal to 0. This 0 will be passed to the input of the second NOR gate. So the result of the second NOR gate becomes 1. Therefore, if set equals to 0 and reset equals to 1, then we get Q equals to 0 and Q prime equal to 1. This value of Q will be stored inside the flip-flop. After this, if set and reset both becomes 0, then the previously stored values won't change. So Q will remain 0 and Q prime will remain as 1. Now, if both set and reset are 1, then firstly, from the AND gates, we will get 1 for both. Next, these two 1s will get passed into two separate NOR gates. So as a result, both Q and Q prime will be 0. But we know that a variable and its complement can never have the same value. So this combination of set and reset is called invalid. Now let's construct a table for the set-reset flip-flop. This table is called the characteristics table. Here we have our inputs set, reset and their operation. Next we have QT. QT signifies the previously stored value inside the flip-flop. It is also called the present state. Next we have QT plus 1. QT plus 1 refers to the output of the flip-flop. So it is called the next state. So when both set and reset are 0, we perform no change. So if present state QT is 0, then the next state QT plus 1 is also 0. And if the value of QT is 1, then the value of QT plus 1 is also 1. If set is 0 and reset is 1, then we perform the reset operation. So the output QT plus 1 becomes 0 regardless of the value of QT. If set is 1 and reset is 0, then for any value of QT, the output will always be 1. So QT plus 1 becomes 1. Finally, if both set and reset are 1, then the operation is called invalid. Now, in order to remove this invalid operation of the set-reset flip-flop, we can use JK flip-flop. JK flip-flop works the same as a SR flip-flop, where J works like set and K works like reset. The only difference between them is the last operation, which is for the combination 1-1. So let's observe the characteristics table for JK flip-flop. We can place J in the sets position and K in the resets position. So the first three operations are the same as set-reset flip-flop. When J and K are both 0, it performs no change. When J and K are 0, 1, it performs reset operation. And finally, when J and K are 1, 0, it performs set operation. Finally, when J and K are both 1, here we use toggle operation. Toggle basically works like a complement. It changes the value that is stored inside the flip-flop. So if the present state QT is 0, then QT plus 1 becomes 1. If QT is 1, then the next state QT plus 1 becomes 0. Now, in order to implement this toggle, we need to make two changes in the circuit diagram of SR flip-flop. So in JK flip-flop, firstly, we use NAND gates in place of AND gates. Next, we pass three inputs inside the NAND gates. The first input is either J or K, the second input is the clock, and the last input is either Q or Q prime. Q and Q prime are basically the present states. Now, let's create the truth table for JK flip-flop. We have three inputs here, the present state, which is QT, J and K. Let's consider QT plus 1 as our next state or the output. For three inputs, we get 8 possible combinations. In the first combination, J and K are both 0. So there is a no change operation. So the value of QT and QT plus 1 will be equal. Since QT is 0 here, QT plus 1 will also be 0. Next we have 0, 1 for JK. Since this is the reset operation, our output QT plus 1 will be 0. In the third combination, J is 1 and K is 0. Since this is the set operation, so the output QT plus 1 becomes 1. In the fourth combination, we get toggle since J and K are both 1. So QT plus 1 will be the complement of QT. Therefore, since QT is 0 here, QT plus 1 becomes 1. Similarly, we can find the value of QT plus 1 for the rest of the combinations. After our truth table is complete, we can get a simplified equation for QT plus 1 using K-map. So our equation for the output of JK flip-flop is QT into K prime plus QT prime into J. This is the equation for our next state using JK flip-flop. So in this video, we have covered the characteristics table, the circuit diagram, and the equation for SR and JK flip-flop. In the next video, we will be covering D and T flip-flop.